Chemical reactions. We've talked about chemical reactions. Chemical reactions always involve chemical changes. So we start out with one or more substances, and then those substances are converted into one or more different substances. What happens in the chemical reaction is that the individual atoms get rearranged. The atoms are not created or destroyed. They are completely unchanged, just like Lego blocks are unchanged when you take something apart and build something new. They're just being rearranged. Chemical equations are a shorthand way of describing chemical reactions. So we put the reactant on the left and the product on the right, just like we read from left to right. And so we're starting here and we're going there. The reactants react to produce the products, okay? There's a lot of information about the chemical reaction found in the equation. We'll have the formulas and the physical states of the reactants and products. We'll get the relative numbers of reactant and product molecules. And then from that information, we can figure out, well, if you start with 10 grams of this, how much of product do you end up? How many grams? And that's a very useful sort of calculation, a practical calculation. These are the, we call them state symbols, how we abbreviate what state a different substance is in. So in parentheses after the formula, G means gas, L means liquid, S means solid, and AQ stands for aqueous, meaning it's dissolved in water. Let's look at the combustion of methane, component of natural gas. So methane gas burns and produces carbon dioxide gas and water in the gas state. Water's in the gas state because when natural gas burns, it's hot, right? And so the water that's formed is in the gas state. So we can write this out using the formula for methane. It's in the gas state. It reacts with oxygen. Oxygen is necessary for anything to burn. Oxygen, O2, in the gas state, because here oxygen is an element by itself, and so the oxygen atoms don't want to be alone. So they're going to go around holding hands, buddy system. Then there's a rearrangement, and now we have carbon dioxide, that's a gas. Here the oxygens are with the carbon, and now some of the other oxygens are with the hydrogen, and they form water. So that's a description of what's happening. But there's a bit of a problem with the description, because on the reactant side we have 2 oxygen atoms. On the product side we have 3 oxygen atoms. Could that happen? Can we start with 2 and end up with 3? No. Yeah, we have to balance the equation. We need to fix the equation. There's something wrong with it. There's something wrong with the hydrogens as well. On the left side we have 4 hydrogen atoms combined in both of these substances, and on the right we only have 2. We can't have 2 hydrogen atoms just disappearing, and they did not turn into the missing oxygen atom. That doesn't happen in chemical reactions. This equation violates the law of conservation of mass, so we got to fix it. So we balance the equation. When we do this, we put coefficients in front of the chemical formulas. We never, ever, ever, ever change the chemical formula. It can be really tempting sometimes. We can't just change this to CH2. And say, okay, well, that's going to fix things. So here are pictures of what's going on here. And it's very helpful to be able to imagine the pictures in your mind to help you understand how this whole balancing thing works. So if we have 2 oxygen molecules, then we are starting off with 4 oxygen molecules. And if we end up, oxygen atoms, 4 oxygen atoms. And then if we have 1 carbon dioxide and 2 water molecules, now we have a total of 4 oxygen atoms. We can't change the H2O and decide, well, we'll just make it hydrogen and leave the oxygen out or something like that. It has to be what it is. And by doing this, then these 4 hydrogens on that carbon, the 4 white balls, have places to go over here, and so it ends up being even. Right? We have the same number of red, blue, there's no blue. Red, white, and black. I was trying to say green. Oh my goodness. It's red, white, and black. We have the same number of little spheres here as we do here. Okay? So we put a coefficient in front, a big number in front of O2. That tells us there are 2 of those. Each molecule is unchanged, it's O2, but we have 2 of them. Over here we're going to get CO2. There's only 1 of them. We don't write ones unless we have to. And then over here, 2 H2O, meaning 2 separate water molecules. Any questions? List of instructions for those who like that. Balancing chemical equations. We need to be able to do this. The first thing is you got to start out with a skeleton equation. So you need the formulas for the reactants and the products and the arrow in there. That's the starting place. After that, this method is called balancing by inspection, meaning we look at it and figure it out. And so I can give you guidelines, but there's no hard and fast set of instructions that if you follow this, it will work out the easiest. So guidelines are to balance atoms that occur in more complex substances first, balance atoms in compounds before atoms in pure elements. You want to leave the elements for last, and the reason is after you've got everything else straightened out, then when you adjust a coefficient on an element, it doesn't mess anything else up. This is kind of a practical thing. If you end up with fractions for coefficients, you need to get rid of those because a balanced chemical equation has the lowest ratio of whole number coefficients. And then you should always check at the end. So we'll do some examples. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. Okay, so this is giving us a description of the reaction in a sentence. So we have to interpret this. So it's a reaction between solid silicon dioxide and, the and is like a plus sign. That's not a good plus sign. Let's do that better. And solid carbon to produce, that's the arrow, solid silicon carbide and carbon monoxide. Okay, so now we've got what's on the left side of the arrow, what's on the right side of the arrow, but we need the chemical formulas. So silicon dioxide. We look at the periodic table and silicon is on the right side of that line. It is a semi-metal, but it's on the non-metal side, and so it falls into the non-metal, the molecular compound way of naming. So silicon dioxide. So that would be SiO2. And it tells us it's a solid, so we should put S in parentheses. Okay? Plus, and I'm going to leave a little space here because I might need to put a coefficient in there. Solid carbon. Carbon is an element. C. You have to ask yourself, is it a diatomic element? No, it isn't. Chlorine is, but carbon isn't. So this is just C by itself. To produce, there's our arrow, solid silicon carbide. I don't know why they put this one in here because we didn't really learn about that one. So I'm going to ask Siri. Hey Siri, what's the formula for silicon carbide?
Okay, I found something on the web for what's the formula for silicon carbide. Take a look.
Oh, that's no fun. Usually she says the formula for silicon carbide is SiC. She pronounces it, and of course she failed me today. It's SiC, S-I-C. There's no way you should know that. Solid. I'll have to have a word with Siri. Carbon monoxide. CO. 1 carbon, 1 oxygen. And that's also a gas. Okay? Any questions about that? Okay, now we need to balance this. A lot of times, if you just start with the first element and work your way across, it seems to work out okay. Here we do have a pure element, so we want to not mess with that one until the very end. But let's look at how many of each things we have on each side of this arrow. So over here, I have one silicon atom, and over there, I've got one silicon atom. So that's good, right? Here in SiO2, I have two oxygen atoms. Over here on the right side, I have to look in all of these, I only have one oxygen atom. So if I write a 2 in front of CO, now I have two oxygen atoms. I can't change that to CO2. That would balance it, help us balance it, but it would change the reaction. It's making carbon monoxide, not carbon dioxide. So now I've got two oxygens over here and two oxygens over there. Now I'm going to look at carbon. So on this side I have one carbon here, and how many carbons in here?
3.
I have 2 here, plus the 1 is 3. So 2 and 3, you both were right, just answering different questions. I have a total of 3 carbons over here, so I need to put a 3 in front of the carbon there. Okay, you see how that works? We're starting with a simple one. We're trying to make sure that we have the same number of atoms of each element on both sides of that line, the arrow. Let's do another one. Write a balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. A lot of gas. Okay, so let's identify from the words where the pluses and the arrow would be. So it combines with oxygen, right? So combining with, that's the plus. To form is the arrow, carbon dioxide and water. So I've got gaseous ethane, and I haven't taught you how to name that, so we give you the formula, C2H6. It says it's a gas, so put G after that. That's going to react with gaseous oxygen. So oxygen is an element. Is it a diatomic element? Yes, it is. I have to write O2. This is why we need to remember which elements are diatomic, and that's a gas. If they didn't tell you that was a gas, how could you figure it out? Well, you might know that oxygen is a gas. It's in the air, right? You can also look on the periodic table. That periodic table on the wall, the colors of the letters are significant. If the element symbol is in red, it's a gas at room temperature. If it's in black, it's a solid at room temperature. And there's 2, bromine and mercury, that are liquids. They're blue, liquids at room temperature. If there's no way of figuring out what the temperature is in the equation, you should just assume that it's at room temperature. So here, oxygen would be a gas at room temperature or at an elevated temperature. So then our products, carbon dioxide, so carbon with 2 oxygens, and we're told that's a gas. And water, so the formula for water is H2O, and we're told that's a gas. Here you do have something burning, and so I would expect that even if you weren't told that it was water, that you could figure out if we're burning natural gas, it's going to be hot and the water will be a gas. So there we've got the formulas, the skeleton. So I'm going to show you a different method than the one we just did. This is helpful to some students, and it's helpful in some situations where things get a little messy. So this is sort of an inventory method of balancing. So I'm just going to draw a line through that arrow because that's going to visually divide the 2 sides that I need to make equal. And then on the left side, I'm just going to list the elements in the order that they show up in the equation. So I've got carbon, I've got hydrogen, and I've got oxygen. And I'm just going to go through and take inventory and see what I've got. So C2H6, I've got 2 carbons, so I'm going to put a 2 here, and I've got 6 hydrogens, and there's no oxygen in that one. None. I used to put zeros, but the zeros and the O's look too much alike, so just a little line there. Here, in this formula, there's no carbon, there's no hydrogen, and there's 2 oxygens. In CO2, how many carbons? And how many hydrogens?
2.
Hydrogen. No hydrogens. And oxygens is 2, right? Yeah, I did that earlier. In H2O, how many carbons? 0. How many hydrogens?
2.
How many oxygens? 1. Okay? I'm just taking inventory to see what I've got. So I'm going to try starting at the top with the carbon. I tend to do that. I just start with the first element. Sometimes you get into it and you feel like you're going in circles and it's not going well. Then just start over and start with something else. Because there are ways that are more difficult and more easy to balance these, and you can't always predict what's going to work. Okay, so carbon, I'm going to look, and I've got 2 plus 0, 2 plus none. So on this side, I have a total of 2 carbons. On this side, I have a total of 1 carbon. So I need there to be 2 carbons on both sides. So how can I fix that? I could put a 2 in front of the CO2. If I had 2 CO2 molecules, now I'm going to have 2 carbons, but it's also going to change the oxygens, right? So I'm going to have a total of 4 oxygens now. It didn't do anything over here. So now my carbons are balanced. Now I want to look at the hydrogen. Here I've got 6 hydrogens and no hydrogens in that one. And over here I've got a total of 2 hydrogens. How can I make a 2 into a 6? Multiply by 3. So if I put 3 here, 3 times 2 is 6, and 3 times 1 is 3. I have 3 of these water molecules. That's like having 3 bicycles, where the hydrogens are the tires and the oxygen is the frame of the bicycle. Then I'm going to have 6 wheels and 3 frames, right? So 6 and 6. And that did not mess up the carbon, so we're good. And now we go down and we look at the oxygen. On this side I have 2, and on this side I have how many? 7. It's not an even number. Dang. Okay, this is where you can use fractions, because if you multiply 2 by the appropriate fraction, you can get 7. Right? If you multiply by 7 halves, you'll get 7. Most students don't like fractions, so I'm not going to show you that, because if you like fractions, you'll figure that one out all by yourself. So this is what I call the odd-even problem. I've got an even number over here. These oxygens are coming in pairs. I have to end up with an even number. There's nothing I can do about that. Over here, I need an odd number of oxygens. How do you make an odd number into an even number? Multiply by 2. You take any odd number, multiply by 2, it becomes an even number. So what I'm going to do is I'm going to multiply everything except this one that I'm working on right now by 2. So I'm going to change colors because it gets kind of confusing. So I'm going to put a 2 here. That makes this a 4 and this a 12. Doesn't change that. I'm going to leave this one alone because that's what I'm trying to figure out. I'm going to change this 2 into a 4. I'm just multiplying everything by 2. And so that becomes 4 of those and 8 of those. I'm going to multiply this by 2. That becomes a 6. And then I've got 12 and 6. Okay, I just doubled everything. My carbons are still balanced. My hydrogens are still balanced. And now with my oxygens, I still have this 2 here because I'm trying to figure out what that coefficient is. But now over here I have a total of 14, which is an even number, And so I can put 7 in front of the O2 and get 14. Any questions? Then you should always go through and double check your work. You got a 6 for the O2? But if you have 6 here, then you only have 12. And you need 8 plus 6 is 14. Yeah. Combustion reactions for hydrocarbons, where you have carbon, hydrogen, and maybe oxygen over here, reacting with oxygen to make CO2 and water. Those are really common types of reactions, and balancing them can get a little funky like this with the odd even business. And so, especially for these problems, making tallies underneath is a good way to keep it straight. Balancing chemical equations that have ionic compounds with polyatomic ions. So the polyatomic ions in many reactions of ionic compounds stay together. They're just switching partners. And if that's the case, then we don't have to balance the individual atoms in the polyatomic ion separately. You may, but you don't have to. So let's look at this one. Write a balanced equation for the reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. So here's my and, that's a plus. And to form is my arrow, and is another plus there. I need chemical formulas for these. These are ionic compounds. I need to write the ions with their charges so I could figure out what the chemical formula is. So here, lead-2 nitrate. What's the formula for lead-2 ion? Pb, 2 plus. Metals always form positive ions. Non-metals are negative. And the Roman numeral here is the charge on the ion. It is not how many of them are in the compound. So it's lead-2. Nitrate, NO3 minus. Okay, some of you are keeping up with that. That's good. You've got to just memorize that. So to put those two together, I need 1 lead ion, and I need 2 nitrate ions. So I'm going to put that in parentheses and put a 2 on the outside. And that's to balance the charges. The charges of these have to add up to 0, so I need 2 of those guys. I'm told that it's aqueous, so I put AQ in parentheses after. Any questions? Then I've got aqueous potassium chloride. This is a metal and a nonmetal. I have another ionic compound. Potassium is K. What's the charge? Positive 1. Because it's in group 1. There's no Roman numeral because it's group 1. We know what it is. And then chloride is Cl. And that's in group 7, so that's a negative 1. Those charges are just opposite in sign but equal in value, and so it's just KCl. That's also aqueous. And here I've got lead-2 chloride, so that's that Pb2 plus again, and the Cl minus. So I need 2 of the chlorides to balance the charge on the lead. I'm going to get Pb, Cl2. Because this is just a single element, not a polyatomic ion, I don't need parentheses. And this word solid tells me it's a solid, so I put S in parentheses after it. And then aqueous, here I've got potassium and nitrate.